Okay, welcome to the class, and we have been discussing SRS for quite some time, and then we'll wind it up today. So we have discussed SRS for single port transmission, and we started discussing it for multi-port transmission, and that's what we'll continue doing that and see how it is different from single port transmission. Okay, so this is a recapture of where we stopped yesterday. Okay, we saw two different examples of multi-port SRS, and in this case, if you see this COM, SRS is a COM, okay, and in this COM, all the four ports, as I said, are mapped onto the same COM. Okay, this green color contains all the four different ports. Okay, and SRS can be generated for a maximum of 4 ports, right? So you see this starting from port number 1000 to port number 1003, okay, all the ports are mapped onto same COM, and the idea of generating different ports on the same COM is basically same as what we discussed for DMRS. Okay, so how do you multiplex different ports on same resource elements? You basically use code division multiplexing, right? Okay, so that's how. So you need 4 different orthogonal codes to map 4 different ports onto it. Okay, so that's how it is done. And this is another example wherein you see this that only 2 ports are mapped on one COM. Okay, right? And so 2 ports on this and 2 ports on this. Okay, of course there is a difference between this and this, that the COM density, okay, has reduced here. Okay, so you can look at it from a perspective wherein, like, if you want to compare this and this, so what have we done? We have basically reduced the resource element density in this case, okay, and then multiplexed 2 different ports on each of this COM, okay, when compared with this, okay, right? So you can call this, I mean, this though is not the right terminology here, but you can call this as FDM plus CDM, frequency division plus code division multiplexing over here when compared with this. Okay, because 2 ports you are mapping on this, 2 ports you are mapping on this. Right? So between these and these ports, what is this? This is like some kind of frequency division multiplexing. Okay, FDM. And on this, it is CDM. You can look at it, but that's not the terminology which is used in context of SRS. Okay? But since we have understood DMRS, this is something similar. Okay, so these are few facts about antenna ports, that they start with 1000 and they go up to 1003. Okay, generally the multiple ports are all multiplexed onto the same COM. Okay, generally that's what happens. Okay, and in order to make this statement more specific, so if these ports are meant for the same user, okay, if one user is has to transmit 4 different ports, so you will multiplex them on the same COM. Okay, and so that's how it is done. So in this case, you'll typically, this kind of allocation is done for different users. So one user will use this COM, another user will use this COM. Okay, and in this case, one user is using all the 4 different ports. Here, one user is using, green user is using 2 ports, and this whatever color, red or, so that is using another 2 ports. Okay. So then we know this now, number of antenna ports can be maximum of 4, and then this is what we saw, so like all 4 ports are mapped to the same COM with a COM spacing of 2. Okay, here COM spacing is 4, and 2 ports are mapped onto each COM. Okay, right, and now we need to study what are these, like how do you multiplex that? Okay, as I said that these 4 ports are basically multiplexed using codes. Okay, what are these codes? Okay, and that's what I'm going to show you. This is something called Z offshoot sequences. Okay, different from the short CDMs which we used. Okay, so what was the length of the sequence plus 4 or 8? Okay, right. So you see this, we are looking. I'm showing you one PRB. Okay. Right, so the way this SRS is allocated, as I said, it can go up to the entire 272 PRBs. Okay, right. So the way you need to generate a sequence which is orthogonal over the entire 272 grid also. Okay, right? Because that's how the SRS is being generated. Okay. Now, so these are the special sequences, okay, which you can generate for like a very you can generate very long orthogonal sequences, okay. And so this is like they're typically called ZC sequences, and you're going to see how they are generated. Okay, so when I'm talking about these ZC sequences, it's basically the orthogonal sequences which we will generate so that you can map out different ports onto a comp. Okay, right? So it is like if it is like a 2-length sequence +1 and +1 -1. But if you have to extend it, you need a generic formula to do that. Okay, and this sequence has very important properties also, as I'll show you. Okay, that's how it is generated. That's all. Okay, but we'll study this. This is the formula. Okay, so what is, you see this? This is a sequence xqi. Okay, what is this? This is a complex exponential. Right, okay, and it contains multiple terms. What is nzc? Nzc is the length of the sequence which you want to generate. Okay, right, and q is the root number. Okay, you will have to fix this number and then generate using this running index. I is a running index. Okay, where it will run from? It will run from 0 to nzc minus 1. Correct? Be able to generate a nzc sequence. Is this clear? How do you decipher this formula? Okay, I is a running index, okay, which runs from 0 to nzc minus 1. Nzc is the length of the sequence, okay. Q is a root number which you will have to fix, okay. So it has very important properties, we'll see, but as of now what I am saying here is these are the 3 parameters over here, okay. So if you have to generate a length 31 sequence, okay, so where will I run from 0 to 30? Right, and q, let's say you fix it to 1, okay, 2, 3, 4, you can fix it like this, okay. So if you fix q is equal to 1, you get one sequence. If you fix q is equal to 2, you get another sequence. You fix q is equal to 30, you get another sequence, okay, right. You cannot fix q as nzc plus 1 because you're going to get the same sequence as the 0th sequence, okay, right. So nzc is the length of the z(2) sequence, and now what is it? You look at this, the properties of this z(2) sequence, okay. So what are we saying? The autocorrelation of a z(2) sequence with a cyclically shifted version of itself is 0. Very important property, okay. And what are we saying? You take a sequence, okay, cyclically shift it, let's say by 1, you correlate it, correlation will come out to 0, orthogonal, okay. Right, so, and this is a fact which is used in assigning it to a different port, okay. Right, so I generate one sequence, I cyclically shift it, I get another sequence, which is, these sequences will follow this property, that's all, okay. But now another property is this, okay, that if you take a discrete Fourier transform, okay, of a z(2) sequence, you get another z(2) sequence, another very important property, okay. Right, you are getting another sequence, and that sequence will also follow this property. Its use will become clear, apparent maybe in the next class or in today's class itself, okay. Right, look at the properties. So very important, okay. I am not able to tell you what is the use of it, but it will become clear, okay. Right, and this is this characterizing parameter q called the root index of the z(2) sequence, okay. Right, and this characterizing parameter q needs to follow certain properties, okay, and let's say, as I said, this is the sequence length nzc, okay. For a given length, the number of root indices generating the unique z(2) sequences equals the number of integers that are relative prime to nzc, okay. So you can only fix q, take q which is relative prime to nzc, okay. Relative prime means the numbers which are not divisible by each other, okay, that's the relative prime, okay, right. So like 4 and 9, they're relative prime, okay. So that's how you, if you are fixing 9, okay, right, what you cannot fix it as 3 and 9 are not relative prime, 4 and 9 are, 5 and 9 are, okay, right, 6 and 9 are not relative prime. So what are we saying? Okay, so this and nzc and q, they are tightly coupled together, okay. And what we are saying here is how many such unique sequences you can generate of a given length. That depends on how many q you can have, right? Okay, correct. So what does it tell? Which values of nzc you will be looking forward for to generate the maximum number of unique z of 2 sequences of a given length. Which values of nzc you will look forward for? Nzc should be a prime number, right? So you can generate maximum number of unique z of 2 sequences. Okay, that's what this bullet is telling. So z of 2 sequences of prime length are of special interest. Nzc should be prime. That's what I am saying here. Okay, because then how many unique z of 2 sequences you will get? You will get, okay, because why do you look forward for? Because they maximize the number of available z of 2 sequences, because you can pick q accordingly. Okay, so for if nzc is prime, okay, how many such unique z of 2 sequences you can create? Nzc minus 1, because q can run from 1 to nzc minus 1, right? For each value of q is going to give you a unique z of 2 sequence. So if it is length 31, you will get 30 different z of 2 sequences of length 31, correct? Okay, if you pick 32, then you don't get, right? You will not get 31 sequences. That's a constraint which is imposed by the design of this z of 2 sequences. Do we understand what am I saying here? Okay, so you can only generate the prime z of 2 sequences of length which has like prime length, okay, and which will give you maximum number of such sequences. Okay, right? So now this leads to another problem, because you look at the kind of resource elements we have, they are not prime in a PRP. Okay, but that's the property of a z of 2 sequence. Okay, we will have to live with that, and we see how that is solved. Okay, because we are using, if we are using z of 2 sequences, you should be able to generate them for even length also. Okay, correct. So what are we saying here? Sequence SRS sequence length MB is always an integer multiple of 12. Okay, because even if it is, you do it over a PRP, okay, that's not the minimum length. You do it over a certain minimum number of PRPs. You assign SRS over a certain minimum number of PRPs. How many PRPs? 4. You remember, right? Okay, so that's what it is. So, and what will be the length? Okay, that's what will be the length of the SRS sequence. Okay, let's see. Just take an example. We studied all these numbers. BSRS 0. That was the first column. Okay, KTC is equal to 4. This is coming over 4, because you remember what KTC was. Okay, and then what is MB? So you put MSRS. If you put SRS for B is equal to BSRS. Okay, if BSRS is 0, what value is this? This is 48, right? And number of subcarriers in a PRB is 12, and then divided by KTC is 4. Okay, so the 144 length sequence you need to generate, SRS sequence you need to generate. Okay, and this is the condition which we need to satisfy. Okay, the SRS should be of this length. It has to be a Z of 2 sequence. Okay, correct. How are you going to do that? Okay, so what the way it is done here is, so a Z of 2 sequence of prime length. Okay, you generate a sequence, prime length sequence which is close to 144. Okay, and then cyclically extend it. Okay, so a Z of 2 sequence of prime length is cyclically extended to a length equal to an integer multiple of 12. Okay, what is it? So how do you do it? So you have generated, as I said, what is this Q? Q we generated in the last slide. Okay, that was a Z of 2 sequence. What is this? N is the index which runs from 0 to MB minus 1. Okay, and this is the sequence. This is the sequence length. Okay, so what is this N mod NZC doing? It is basically extending the sequence to, it is cyclically extending the sequence. What is happening over here? Okay, once you basically exceed NZC, right, what are we saying? We'll start reading back the 0th bit, right? So that's the cyclical extension. Is this fine? Okay, so what are we saying? So what is this? How do you pick NZC? NZC is the largest prime number such that NZC is less than MB. Okay, correct. So if it is 144, you pick up the largest prime number which is less than 144. Okay, correct. And then you generate the NZC Z of u sequence for that length and then cyclically extend it. Okay, right. And then there's certain other property, certain other facts about this sequence. So multiple sequence for a given length are organized into 30 different sequence groups. Okay, and where u, which is, you can generate so many sequences, right? Okay, that is like depends on the what NZC you are picking. Okay, so you basically arrange these sequences into 30 different sequence groups. That's what is this u coming over here. Okay, and v is the indexes the sequences within a group. Okay, I'm not going to go to the detail of how they are arranged into sequence and how do you basically first arrange into a sequence group and then take the index the sequence within a group. This is a little involved to be covered here, so I'm not going into the detail of this. But the key fact which I am telling you here is that Z of u sequences, okay, the way they are generated, you have to generate them for the prime length. Okay, and this is a constraint which is imposed because that's how the PRB structure is, and then you cyclically extend it, and that's what is going to give you the desired length Z of u sequence. Okay, fine. So this is how these orthogonal Z of u sequences they are generated. Okay, then what happens? Okay, so for SRS supporting more than one antenna port, okay, different ports share same resource element and the same basic SRS sequence. Okay, same basic SRS sequence means you generate one sequence. Okay, use that as a base sequence for one port. What happens to how will you generate other sequence? What was the property which I told you about the Z of u sequence? You cyclically shift one sequence, you get another sequence. Okay, right? That's what we are doing. So different phase rotations are then applied to the separate different port. The phase rotation, if you do, what does that do? It's basically in other domain, it will give you a cyclically shifted phase shift sequence. Okay, so that's how you are doing it. Okay, so this is a base sequence. Okay, right? MB length sequence. You are basically phase shifting it by some alpha, right? Okay, so what happens? Phase rotation. You are doing this phase rotation where you do the entire processing in the frequency domain, right? Okay, and this phase rotation in frequency domain, what does it, if you rotate the phase in frequency domain, it will correspond to a cyclic shift in the time domain, correct? Okay, this is basic DSP. Okay, right? And why am I suddenly bringing the time domain over here? I'll explain it to you. Okay, so what are we saying here? That you generate one sequence, okay, then you cyclically you do the phase rotation of it. Okay, this phase rotation will correspond to a cyclic shift in the time domain. Okay, correct? And why am I not doing this cyclic shift here? Wait for it, I'll give you the answer. Okay, because the way we understand here is these SRS, okay, for different ports, they are commonly used to estimate channel in the time domain, not in the frequency domain. Okay, that's what is my understanding. Okay, and what happens here? So if I gave you another property that if you take the DFT of a Z of u sequence, you get another Z of u sequence. Okay, so this is one Z of u sequence in time domain. Multiplied by phase, you get another cyclically shifted phase sequence in time domain. Okay, so in time domain, these two you will get two cyclically shifted Z of u sequences. Okay, which will be used for two different ports. So you give a different phase shift, you will get another cyclically shifted sequence. So that's how you generate, and you use them for 4 different ports. Okay, or 2 different ports depending on how many ports are assigned. Okay, fine. So this is basically, so sequence is RLP, that's what you have generated. Okay, what is the length of this? This is length MB, is mapped onto the Lth OFDM symbol of the SRS sequence. Fine. Okay, so now, so to recapture, how have we basically generated these SRS sequence for a multi-port SRS design? Okay, first of all, understand this, that whatever we discussed before this was a single port Okay, we did not generate any SRS sequence there. Okay, this was one sequence which we were using for one user, this was another sequence which we were using for another user. Okay, and all of them were doing single port transmission. Okay, let's say each user has to do multi-port SRS transmission. That's what this class is covering. Okay, and what we are saying here is on the same COM, okay, you multiplex multi-port SRS transmission. Okay, and how is this multiplexing done? This is done by generating a suitable length Z of shoe sequence. Okay, and this Z of shoe sequence has certain properties. Okay, two properties. Okay, one is that its DFT gives you another Z of shoe sequence. Okay, and the second property was you cyclically extend it. Okay, or the cyclically shifted version of it. Okay, the cross correlation is 0. Fine. Okay. So, why are we talking about time domain? Okay, how is this cyclically shifted sequence useful there? That's what I'm going to show you. Okay, that's the example I'm taking. So this example again, we have picked up the old example. Okay, you remember how did we discuss the use of SRS? Okay, so what we said was like to estimate H. Okay, UE will transmit NB is equal to 2 orthogonal SRS. I am taking that old example wherein the user has two antennas, okay, right, and it is transmitting a 2-port SRS, correct? Okay, and what we said over here was assume that channel remains constant over 2 subcarriers, right? Okay, we use this property. How did we use that? You remember that on first subcarrier UE transmits this SRS 1 1. On second subcarrier, UE will transmit this. Okay, but what we said there was this SRS is limited to 2 length. Okay, only 2 resource elements. Okay, and what we assumed over there was the channel remains constant. Okay, correct. Now this is what. So what is happening? So this SRS is orthogonal over 2 subcarriers. That's what is happening. And how are you using this fact over here? Assuming that this channel remains constant over 2 subcarriers, what happens? Okay, so the received pilots on the first and second subcarrier, how do they look like? Okay, this is you transmit. This is our system model. Okay, Y A is equal to H P A plus N A. This is our typical system model. Y is equal to H X plus N. Now X is P A. Okay, and this is the Ath subcarrier or the first subcarrier. This is the Bth or the second subcarrier. Okay, you are transmitting this PB over the second subcarrier, right? Okay. Now, how did we estimate this channel? What did we do? Okay, we concatenated these two, right? And we got this equation, correct? Okay. And what is, then we took this common H, okay, fine, right? And the system of equations become like this, correct? Okay. Now, how are we able to write this or this or this? We assume this channel is constant over 2 subcarriers, correct? Okay, and with this you are able to write this HP plus N. Okay, and what happens over here? You multiply this YPH. Okay, you multiply it from right with P Hermitian. Okay, and you get Y tilde, which gives H plus N. Same statistics. Correct? Okay. What are the key assumption here? Assumption is H is constant over 2 subcarriers, right? And that's how you are able to pull it out from here, and you are using this orthogonal. P is an orthogonal matrix, correct? What happens if H is not constant over these 2 subcarriers? Can you estimate if it is HA and HB? Okay, can you estimate HA and HB from these 2 equations? It will become an underdetermined system in the sense that number of variables HA and HB is more than the number of equations you have. Okay, right? So you look at this. Again, this is if how many elements it has? It has only 4 elements. It's a 2 cross 2 matrix. Okay, H. Okay, right? If it is a number of received antennas is 2. Okay. Correct. So H will become a 2 cross 2 matrix. Okay. So you have, if you look at, so it's a 4 element, and then you look at this, there will be 4 equations sitting over here. Okay, because YA is 2 cross 1, YB is 2 cross 1. Okay, so basically 4 equations, okay, and you are able to estimate 4 variables from that. Okay. Now if HA, it is not like this, if H is not constant, okay, it becomes HA and HB, so you cannot estimate it, right, okay. So the key property here is that H is basically constant over 2 subcarriers. Now what are we talking about SRS, okay, right. So what is SRS estimating? What is the objective of SRS? Minimum, you remember how many, it can send it over, the SRS is configured to send it over 4 PRBs, okay. Okay. So there the channel can be constant, 1 PRB, 2 PRBs, 4 PRB. You can, 4 PRB is still a reduced bandwidth, is a small bandwidth, okay. 1 PRB is how much? 30 into 12, 360 kilohertz, okay, right, and 360 into 4, around 1.4 megahertz, okay, still small bandwidth. Now if you have to basically, SRS is configured to estimate the channel over entire band, correct, it can be configured, right, then can you assume this H to be constant over the entire band, right, okay. It is not, because it is a 100 megahertz channel, right, so H cannot be assumed to be constant. Then how will you do this exercise? How will you pull out H from it in the frequency domain, right, okay. So you basically, we cannot do this, right. If H is not constant, you will have to, and you are planning to estimate H over the entire band, okay. So it will become our, like, this operation fails, okay. This is not a useful way of estimating the entire broadband channel over 100 megahertz, which is changing across frequencies, because this becomes, even though PA and PB, over one port you transmit, let's say this 270, whatever is the length, okay, you use one orthogonal sequence here, you use another orthogonal sequence for the second port, okay. But if channel is not constant, how will you estimate? How will you bring in, how this H is, it will become HA, PA, HB, PB, right, okay, correct. And this is something where that time domain property comes into picture, okay. So what happens there is, okay, so if it is, so SRS is orthogonal over the complete resource in the frequency domain where channel is not orthogonal, correct, okay. Now if you look at the, if you have to estimate the entire broadband channel, okay, so typically what is the way it is estimated using SRS is, okay, so if you look at the time domain channel, okay, I don't know how much you are familiar with the time domain channel, okay, what happens there is a typical wireless property that it is limited to a certain delay, okay, right, and so it will be something like, there will be only few taps which will be non-zero, okay, rest of the taps are going to be 0, fine, okay. Now you have to estimate channels of 2 different ports, okay. So the way you are going to do here, and I am just giving you a overview of how it is done. If you have to refer to this, what I am explaining now, you will have to refer to this paper, okay. So what happens is, so one port channel, you have used one SRS, okay, correct, and another port channel you have cyclically shifted it, okay, right. So time domain channel is limited to few taps, okay. So one SRS port will give you this, okay, another port is cyclically shifted, so it is going to give you a cyclically shifted channel, okay, right. So what happens, okay, so if it is, I don't have the pen today, okay, so I should have used that, okay. So few taps, 10 taps, let's just assume that, okay, the time domain is the 10 tap channel, okay, SRS 1 will estimate that, SRS 2 is a cyclically shifted version of that. So the channel you are going to estimate is a cyclic, so for the port 2, it will be cyclically shifted version, okay. So if you take 2 SRS, okay, whose cyclic shift is more than the duration of the time domain channel, okay, right. So what happens here is that the second SRS, will estimate that channel because it is cyclically shifted version of it, okay, and they will not interfere because you have shifted the channel in the time domain using this cyclically shifted SRS, okay. So you basically estimate these two channels in time domain, okay, and then filter them in the time domain and bring it back the second one because it's a cyclically shifted version, okay, right. That's how you basically do this channel estimation for SRS. If you want to understand more about it, you have to read this paper, okay, wherein like you make these channels which are not orthogonal in frequency domain using the cyclically shifted version. You make them orthogonal in time domain, estimate them there, then bring them back to frequency domain. That's the key idea, okay. Now you see the use, okay, that SRS, why a DFT of SRS should be another SRS sequence, okay, because this if you want to exploit this property, you should get another SRS sequence in the time domain, right, okay. So, and that's a key property when you have to basically estimate a broadband channel where the channel is not constant, okay. So if you are estimating a few narrow band over a few PRBs, you can still do whatever we did here, but if it is a estimation over a broadband channel, then this kind of estimation fails, and then you have to go to the time domain and these properties become useful, okay, right. What were the two properties? That cyclically shifted version of it has a zero correlation, plus DFT of a Z of shoe sequence gives another Z of shoe sequence, okay. That property is useful here, okay, right. So I gave you a basically bird eye view of how it can be done and how the channel estimation can be done in time domain, okay, because using this cyclically shifted sequences, you can artificially create time domain channels which are not interfering with each other, okay. So you estimate the channel there, bring them back to frequency domain, okay. So this brings us to a closure of SRS discussion. So next topic will be CSIRS. That's the only thing left with respect to our pilot discussion. We have discussed DMRS, we have discussed SRS, okay. So CSIRS will begin in the next class. Thank you.